Have you ever looked at the night sky through a standard pair of binoculars? You see the stars and constellations, and they look beautiful. But then, you look at images from the Hubble Telescope. Suddenly, those tiny points of light aren't just dots. You see the rings of a planet, or the swirling gases of a nebula light years away. You realize that what you thought was resolution was just a blurry approximation of the truth. In analytical science, most mass spectrometers are like those binoculars. They tell you the nominal mass. But if you want to see the ultimate truth, you need the FT-ICR. Welcome to Module 8-1, the Hubble Telescope of Mass Spec. To truly grasp the power of FT-ICR, we must start with a fundamental paradigm shift. In other analyzers like quadrupoles or time of flights, ions are always on the move, racing toward a detector. But in ion cyclotron resonance, or ICR, we do something radically different. We stop them. We trap the ions inside a specialized cubic cell held within a powerful superconducting magnetic field, denoted as B0. When a charged ion enters this field, the Lorentz force bends its path into a circle. This is cyclotron motion. The ions are effectively imprisoned in an endless loop. Instead of measuring how fast an ion flies across a room, we measure how fast it spins in its cage. Now let's look at the high-performance logic behind this trap. Every ion is spinning, but not at the same speed. Think of these ions like figure skaters spinning on a smooth ice rink. Their tempo, or angular velocity, is determined by the magnetic field, the charge of the ion, and the mass. Look at our core equation. Frequency equals charge times the magnetic field strength, divided by the quantity 2 times pi times mass. Notice that mass is in the denominator. This is crucial. It means the smaller the mass, the faster the skater spins. Because the field and charge are known constants, if we measure the frequency with high accuracy, we calculate the mass with incredible precision. In FT-ICR, frequency is our currency. Here is the challenge. When ions are first trapped, they spin in tiny microscopic orbits near the center of the cell. They are so far from the detection plates that we can't actually hear them. It's like someone whispering at the other end of a football stadium. We need them to move closer to the walls, the detection plates, without letting them escape. This is where we use resonant excitation. We apply a radio frequency pulse to the cell. If the pulse matches the cyclotron frequency of the ion absorbs that energy and its orbital radius increases. Like pushing a child on a swing at exactly the right moment, the ions move higher and higher until they are spinning in a large coherent packet, ready to perform their song. This represents the height of analytical maturity. In other mass spectrometers, the ion's journey ends in a crash where the sample is destroyed. But in FT-ICR, we don't hit a detector. We listen. As that coherent packet of ions spins past the metal detection plates, it induces a tiny electrical current, called an image current. The ions are literally singing their mass to us. Because this process is non-destructive, the ions stay in their orbit and continue to spin. We can listen to this song for several seconds. The longer we listen, the more detail we get. This is why FT-ICR can identify mass differences down to the 6th decimal place. We observe the truth without destroying it. However, reality is rarely simple. In a real-world sample, you have thousands of different ions spinning in that cell, all singing at the exact same time. What we record on our plates isn't a single clear note. It's a chaotic, overlapping mess of waves. We call this the free induction decay, or FID. It is a signal recorded in the time domain. Imagine standing in a cathedral where 100 different choirs are singing different songs all at once. To the untrained ear, it's just noise. But within that noise is the ultimate truth of your sample. Our challenge is to pull that choir apart and turn that chaotic signal into a precise list of masses. This is where we apply the mathematician's magic, the Fourier transform. The FT is a sophisticated mathematical filter that can take a chaotic choir of overlapping frequencies and instantly pull them apart. It is the bridge between what we hear and what we know. The FT identifies each specific frequency within the messy wave. Because our equation tells us that frequency is tied to mass, the Fourier transform effectively turns that time domain signal into a clean, high-resolution mass spectrum. It takes a signal that looks like gibberish and transforms it into distinct, accurate peaks. We have successfully decoded the ion's song. Now, for the perfectionists. High resolution is one thing, but absolute accuracy is another. To get world-class results, we deal with a technical nuance called phase correction. In a real ICR cell, not all ions start their dance at the exact same moment. This slight desynchronization can lead to phase distortions, broadened peaks that ruin your sixth decimal place accuracy. By applying sophisticated phase correction algorithms, we align the signal components to produce absorption mode peaks. These are significantly sharper, providing twice the resolving power compared to standard processing. It's the difference between seeing a blur and seeing the individual atoms. Combined with massive superconducting magnets, this is how we achieve the absolute pinnacle of mass spec expertise. Let's wrap up this deep space audit. Today we've learned that FT-ICR is the Hubble Telescope of our laboratory. We've seen how the magnetic prison traps ions so we can measure their cyclotron frequency. Remember, frequency equals charge times field strength divided by 2 pi times mass. We've discussed resonant excitation and how we listen to the ion's song through the non-destructive image current. Finally, we saw the magic of the Fourier transform, turning chaotic waves into high-resolution data. FT-ICR is a statement that in science, every decimal place matters. You can now see the ultimate truth of the molecular world. But I know what you're thinking. This sounds amazing, but I don't have a room-sized magnet and $5 million in the budget? You're right. FT-ICR is a massive investment. However, the story of high resolution didn't end there. In our next unit, Module 8-2, the Benchtop King, we're going to meet the technology that brought this high-resolution power to the everyday lab bench. We are going to look at the Orbitrap. It uses many of the same principles of frequency and Fourier transforms, but in a package that fits right next to your HPLC. Take a breath, review your notes, and I'll see you at the bench for our deep dive into the Orbitrap.